this video, I'll try to review the graphical method of acceleration analysis. So if we have a link that is rotating about this pivot, which I'll mark as A, there's a point P on the link. We have uh, a vector RP representing the position of the link, and if this is at an angle theta, then, and let's say this is of magnitude p, small p, this is equal to p e to the j theta. We know the velocity of p is the derivative of rp, which is j p omega e to the j theta, and which suggests that this is at 90 degrees to the position. We can also find absolute acceleration of point P as the derivative of the vector Vp, and this is equal to jp alpha e to the j theta plus j square p omega square e to the j theta, and this is simply equal to j p alpha e to the j theta minus p omega square e to the j theta. So we said in the class that this component is the tangential acceleration of the point P, and this component is the normal acceleration of point P. The multiplication with J suggests that for a position vector of this type, there is a 90-degree rotation at which the tangential acceleration vector is, and then there is a vector which is exactly opposite in direction to the position vector. That's the normal acceleration. The normal acceleration is pointing towards the center of rotation. This we can apply to the 4-bar linkages to do the graphical acceleration analysis. We will quickly also say if there's a sliding block on which there is this link and the block is going with an acceleration of a, that just means that if we want to get to the acceleration of point P, we have to first consider P with respect to A and then add the acceleration of point A itself. So this can also be written as acceleration of P normal plus acceleration of P tangential, and then these both are with respect to A, and then we can write acceleration of A to be the extra term that needs to be added. The other case that we've also considered is that if there is a link which is rotating and there is a slot in the link such that there is a slider which can move inside the slot, and this is the point P, this is the point A, then the position RP is, while it is still P e to the j theta, P is variable. So we get Vp to be equal to P dot e to the j theta summed with j p omega e to the j theta, which means now the velocity can be in along the slider as well as orthogonal to the point 90 point at the given position. And so the total net velocity of this point P as observed from A will be sum of Vp slip and Vp transmission. These are both with respect to this fixed pivot. And then when we consider the acceleration of this point, we get P double dot e to the j theta plus 2 omega P uh, j P to the j theta plus uh, minus 1 P omega square e to the j theta. jp dot. Yeah. So we said this is again acceleration of slip. We said this is I've missed out on one more term. There should be uh, jp alpha e to the j theta, because this will end up giving us three terms, one of which gets combined into this term. So this is absolute. This is acceleration of slip. This is the Coriolis component, which occurs only when a sliding member is on a rotating link. And then this is the usual A normal, and this is the A tangential. All right, so to complete this discussion, I'll quickly point out what are the different velocities considered in the 4 bar. And we have these pivots, 1, 2, 3. This is grounded. This is grounded. We see for O2, A, B, O4, considering there is omega and alpha 2, and this is at an angle theta 2. From position analysis, we have already obtained theta 3 and theta 4, and from acceleration analysis, we have obtained omega 3 and omega 4. We are trying to find in acceleration analysis what are alpha 3 and alpha 4, and we can draw this as A alpha, or maybe I'll just mark those as the acceleration of A tangential. This is acceleration of A normal. We know this acceleration of B with respect to A normal. We don't know the acceleration of B with respect to a tangential in magnitude, but we know that it has to be perpendicular to AB. And then similarly, so this is line of acceleration of B with respect to a tangential. Here we know acceleration of B with respect to O4 normal, and we know that this should be the line of acceleration of B tangential. We can take all of these and draw them on on an acceleration diagram. We get that's acceleration of A normal. There is acceleration of A tangential, and the sum of these two is the acceleration of A absolute. From this point, we get uh, the acceleration of B with respect to A normal, and we go back to the origin and we draw acceleration of uh, B normal, and from here we know we have a dashed line representing the L A B with respect to a tangential, and another line to say that's let's just say that's acceleration of B. This is line of acceleration of B tangential. So this would be the point. That would be the acceleration of B tangential, and then there would be this velocity or acceleration, which is acceleration of B with respect to A tangential. And so for both these cases, we can draw the full vector. This will be acceleration of B with respect to A, and This will be acceleration of B. From here, we can identify, for instance, alpha 4 would be equal to magnitude of acceleration of B tangential divided by the length of the link, that is C, and alpha 3 would be acceleration of B with respect to A tangential divided by length of the link B. You can also consider the case where these are rigid objects. There's this pivot. The links are having a certain shape, and then we can pivot them here and here. Grounded link 1, this is link 2, 3, and 4, and we can then pick up any point arbitrarily, say here, and say this is um, at some distance, maybe P, and has an angle delta 3. We know acceleration of this point P here. This is magnitude of this position vector here. Locally, P is acceleration of P with respect to A uh, plus acceleration of A. We can write that, and then we can also write this is completely known once we finish the graphical analysis. Acceleration of P with respect to A can be written as the link length P times alpha J. This is third alpha of the third link, which we have identified from the acceleration analysis. And this is e to the j theta 3 plus delta 3. And we have minus p omega 3 square e to the j theta 3 plus delta 3, and then acceleration of A. That you can use a similar approach to identify any point on either link 2 or link 4. You have to just consider what is the absolute acceleration that you already know, and then you can use the angular acceleration of the link on which the point resides, or the angular velocity of the link on which the point resides, and then consider the angle at which the point is positioned. So that is all about the acceleration analysis and using the graphical method for 4-bar. You can extend these concepts to a slider crank or other linkage, uh, and obtain the accelerations at various points on the links.